Putting something together yourself can be a really satisfying experience, whether it's a recipe, a tool shed, or of course, your own PC. But ordering parts from your favorite website and slotting them together is really as far as most people go. I mean, you can't exactly whip up a CPU from scratch, can you? Well, you can't. But fortunately, companies like Intel, GlobalFoundries, and TSMC do it every day. But how? Believe it or not, the main ingredient in that fancy Core i7 sitting in your rig or that Snapdragon sitting in your smartphone is sand. I mean, it isn't exactly the same stuff that you find on the beach. It's specially mined in order to be more pure than what you would make a sandcastle out of. And this sand is heated to thousands of degrees and chemically purified to produce a virtually flawless cylinder of silicon, hence the name Silicon Valley for California's high-tech region. Now, the reason that purity is so important is that as processor technology has continued to advance, the tiny transistors on CPUs have gotten smaller and smaller so that more of them can fit on one processor die, making it more powerful. And because chip makers are now packing as many of these transistors as possible onto CPUs, the margins for error are extremely slim, making precise manufacturing and ultra-clean environments absolute musts. So after the silicon is purified, it's cut into what are called wafers, which resemble mirrors more than the cracker kind of wafer. That wafer is then polished, a photosensitive chemical is applied, kind of like what's used in film, then ultraviolet light is shone through a stencil that's shaped exactly like the transistor layout that the engineers created for the CPU. Because wafers themselves are usually quite large, the process of shining light through the stencil can be repeated many times, fitting hundreds of CPU dies onto a single wafer. After the UV light step is complete, the wafer is washed in a solvent that dissolves the exposed areas, leaving a pattern that another machine etches into the wafer itself. These etches are then bombarded by ions, charged atoms that embed themselves into the silicon, changing the way that they conduct electricity to create transistors that only allow current to flow in one direction, which means they can function as tiny switches or gates that make your CPU able to understand instructions, which, by the way, you can learn more about here. In fact, the whole reason we use silicon as the base for processors is because of its ability to accept these ions that form the foundation for modern transistors. So after these transistors are created, the next step is to connect them together to make a functional processor die. This is done with rigid copper interconnects, essentially tiny wires that are applied on top of the transistors with a similar ultraviolet and etching process to what I explained earlier. Exactly how they're connected depends on what CPU architecture the engineers are using, whether it be something like Skylake, codename Skylake for Intel, or codename Zen for AMD. This is done in many, many layers to prevent any of these wires from accidentally touching and causing a short circuit or any other kind of defect. The dies are then tested, and the good ones are placed into a CPU package. That is what allows it to plug into the socket on your motherboard. You add a heat spreader on top of that, and voila! You've got the beating heart of your new PC, phone, or anything else that requires a CPU. But is silicon always going to be the core ingredient in the buffet of CPUs of life? Well, because of the chemical properties of silicon, actually, the answer is probably no. We're very close to the physical limit of how small transistors can be made on silicon, meaning that we may see CPUs made from something completely different by the end of this decade. But silicon will remain very useful for quite some time, and besides, renaming the Bay Area Indium Gallium Arsenide Valley just doesn't really roll off the tongue. But you know what does roll off the tongue? Fresh books. Fresh books. Fresh books. The irony being that while the idea is fresh, Books are really not what we're talking about because it's all in the cloud. I mean, okay, it's doing your accounting books, so figuratively there. But anyway, the point is, FreshBooks is all about small business owners who want to get more organized, be able to make more money because they can spend their time doing actual work instead of, chasing down invoices and figuring out how many hours they build on that job. And whether you're a, dance instructor, a yoga teacher, a plumber, a house painter, a computer technician, or whatever it is that you're doing as a small self-employed person, FreshBooks is going to make your life less stressed out and more organized. You can track all of your hours in one cloud-managed place. You can create invoices. You can send them to clients. You can see when they viewed your invoices, and they can pay you directly through invoice. They've even got a new feature that allows you to accept deposits through their platform, so you can make sure you don't show up on a job site with a bunch of, pipes and toilets and have the client be like, yeah, so we went with someone else. Deposits are a much bigger thing than you might necessarily think. Now, getting started on FreshBooks is extremely simple, even if you're not a numbers person, actually, especially if you're not a numbers person, and you can try FreshBooks for free for 30 days by going to freshbooks.com/TechQuickie and entering TechQuickie in the How Did You Hear About Us section. It's linked in the video description. So thanks for watching, guys. If you liked the video, like it. If you disliked it, well, I'm sorry to hear that, but I guess you can dislike the video. Check out our other channels, by the way. We have a video coming very soon on Channel Superfun. You're going to want to get subscribed to Channel Superfun because it's awesome, where we this is kind of it's kind of like a spoilers thing. Okay, well, whatever. We build lightsabers. It's really freaking cool. Guys, leave a comment under this video if you have suggestions for future fastest possible videos. And as always, don't forget to subscribe and follow and all that good stuff.
Welcome back to Computer Hardware, Bits and Bytes. This is an introduction to Unit 3, the CPU. So you're on your computer, and all of a sudden, you need to figure out 93 plus 42. And you don't feel like doing it in your head. So you make the computer do it. But what does the computer do? What happens in its head? For the answer to this question, we journey into the brains of any modern computer, the CPU. CPU stands for Central Processing Unit. You can think of it like a computer's brain, and it works kind of like ours. We'll take a look together at the different structures inside a CPU and connect them to structures we have inside our brains. First off, it has working memory, except called registers. And while us humans can only store 5 to 9 things in our limited working memory, a computer usually has up to 32 things at once. And by things, I mean a collection of zeros and ones, representing a number. So most all the data that a computer processes first must pass through these 32 registers. Second, there is the logical mind of the computer, which is called the Arithmetic Logical Unit, or ALU for short. This is where the data and the registers are actually manipulated. The ALU usually takes 2 numbers from the registers and combines them in some way. Some of these combinations are mathematical, like add and subtract, and others are logical, like and or. And then, it puts the result back into a register. So for any operations that are mathematical or logical, which is actually most of what a computer does, the data will go through the ALU. What happens when us humans run out of working memory? Well, we have long-term memory. In a computer, this is called random access memory, most commonly known as RAM. And when we run out of registers, we can move our information into the RAM. Also, RAM is where most of the memory is located for the current tasks at hand, so we can move it back into the registers for our working memory. RAM, registers, and the ALU. Pretty much everything a computer processes flows through these 3 structures. So these parts of the computer work together to form the basis of the CPU. Let's test your knowledge. Question 1. Can you name the 3 CPU parts we talked about so far? If you said RAM, registers, and ALU, you are correct. Question 2, related to our example. Where would we add 2 numbers? The ALU, or Arithmetic Logic Unit, is correct. Nice work. Alright, this is cool, but isn't there some magic missing here? How does the computer know what to do? So computers do all these crazy things and seem really smart, while in reality they are not so smart because they can only do what they're instructed to. So part of the RAM is filled with instructions, which we call the program memory part of it. So all that code that computer programmers write is split up into bite-sized chunks and put here into program memory. It's just like other memory, except that the computer knows it has instructions instead of numbers or letters. So what can we tell the computer to do? All the instructions that a computer has are defined in the CPU's instruction set. There are three main types of instructions. Some use the ALU with numbers from the registers, like add and subtract. Others move data from registers to RAM and back. For example, the load instruction can move data from the RAM to the registers, and store does the opposite. And the last type of instructions change the way that the program flows. So if you add a number 50 times, you can just have one line telling it to do that 50 times instead of 50 add instructions. We'll focus mostly on the first two categories. Now let's move to question 3. How does a computer know what to do? If you said instructions or we tell it to, that's right. Question 4, relating to our example. Where do numbers need to be so that we can add them in the ALU? That's right, the registers, because the add instruction only works from the registers to the ALU. Now let's go back to look at how all these parts work together to solve our little math problem, 93 plus 42. Well, first, these numbers we punched in are somewhere in RAM, except now they look like zeros and ones in their binary version. Still the same number though, and they are in their own spot in memory, labeled FF00 and FF01. These spots are called their address. Yep, almost like they live there. And then we have the RAM, with the two numbers in it at their addresses, and also the registers. So ultimately, to add the numbers, we need them in the registers, right? How would we do that? Let's see if you know. Question 5. How do we tell the computer to move the numbers from RAM to the registers? The load instruction is how we do it. So we tell the computer to move the numbers from memory to the registers by two load instructions. So the 93 in FF00 goes to R0, and the 42 in FF01 goes to R1. Question 6. How would we tell the computer to add the numbers? If you said an add instruction, that's right. Remember, the computer can only do what we tell it to. So the next instruction we execute is adding R0 and R1 in our handy ALU. So it moves R0 and R1, adds the numbers, and then outputs it back into the registers. So now the computer has calculated 93 plus 42 and spits out 135. Wow, a lot happened just for one simple thing. And now, you know some of the brains behind the CPU. Hope you stored something from your registers to your RAM today, if you know what I'm saying.